Hi class, today we are going to look at mAFL, a non-intrusive semi-hosted extension to AFL for fuzzing embedded device firmware. It is based on the paper that was published in the 44th International Conference on Software Engineering. Today, embedded devices are ubiquitous. They can be found everywhere, from military asset tracking and remote patient monitoring to edge computing-enabled wearables and self-driving cars. As this chart illustrates, it is projected to become a trillion-dollar industry in the next 4 years. In 2025, IoT devices collectively held 79 zettabytes of data, underscoring the accelerating scale of information generated and stored across embedded devices. Embedded computing research has led to very powerful and energy-efficient IoT architectures, enabling edge computing and smart home applications, which implies that any vulnerability in these devices can be a threat to society at large, as well as at an individual level. Moreover, these devices are a treasure trove of sensitive information. In the recent years, escalation of these vulnerabilities to large-scale attacks demonstrates the importance of testing embedded and IoT applications for vulnerabilities and bugs before deployment. So, the term fuzzing was introduced in 1988 by Barton Miller at the University of Wisconsin-Madison as part of a class project. The project was designed to test the reliability of Unix command line programs by executing a large number of random inputs in quick succession until they crashed. Miller's team was able to crash 25 to 33% of the utilities they tested. They then debugged each of the crashes to determine the cause and categorized each detected failure. In the 1990s, fuzzing mainly involved random input generation, without understanding program structure. While primitive, these early fuzzers were surprisingly effective at uncovering crashes, buffer overflows, and input validation bugs. From 2000 onwards, that's where the real progress happened. Fuzz testing evolved into more sophisticated forms such as mutation-based, generation-based, and coverage-guided fuzzing. Tools like AFL, the American Fuzzy Lob, used runtime feedback to systematically explore program paths, making fuzzing a core technique in modern security and testing pipelines. Today, fuzzing is an automated software testing technique which works by supplying a system under test with random unexpected inputs and monitoring it for any unexpected outcomes or scenarios. These unexpected outcomes or scenarios vary with the system under test and the goal of the fuzzing user. The fundamental building blocks of a mutation-based coverage-guided gray box fuzzer look as follows. A seed pool consisting of initial set of inputs to mutate off of. These inputs are generally selected for their good semantics and coverage increasing properties, so the fuzzer does not waste the initial time generating random inputs that get rejected immediately. A seed scheduling algorithm which decides how seeds are selected. This can be random. A mutation engine which mutates the selected seed using various mutation strategies. The target binary, instrumented with coverage tracing and fault detection runtime hooks. The mutated input is provided to the instrumented binary. The program execution returns coverage feedback, which dictates which inputs are interesting and which can be discarded. On detection of a bug or crash, the input is safe for later triaging. However, it is not straightforward adapting this fuzzing loop to embedded applications for the following reasons. Embedded devices have limited memory and computational resources to store the seed pool, perform mutations, and coverage analysis, which form the core of the fuzzing loop. Embedded architectures are diverse and differ from device to device. Moreover, operating system support is also highly dependent on the platform, as shown here. There are so many different types of software and hardware supported by different microcontrollers and vendors. In many cases, the embedded device does not even possess any operating system running firmware on bare metal. These minimalistic designs, as such, do not possess the facilities required by fuzzing that we take for granted in a desktop environment. To solve this challenge, early works proposed rehosting the embedded application on a more powerful desktop. In this setting, the microcontroller hardware is emulated on the workstation through sophisticated techniques. As such, both the fuzzing and execution of the target binary happens on the desktop device. Some later works extend this idea to add the MCU hardware in the fuzzing loop, where certain parts of the firmware that interact with the hardware are hooked and executed on the actual MCU, while executing other parts on the workstation emulator. Again, in this case, the most of the target execution happens on the workstation. However, this approach to fuzz testing embedded applications has some obvious pitfalls. First, rehosting based on software emulation inevitably approximates the behavior of real hardware at its best. This approximation compromises the fidelity of the firmware-hardware interactions and precludes the identification of firmware issues that are closely associated with hardware behavior. The fault detection techniques of current rehosted solutions are based on experimental-only methods, require considerable engineering effort, or only provide coarse-grained detection capabilities. Even if rehosting techniques might provide synthetically good coverage over time, they are limited to detecting specific faults when they occur. Finally, software emulation lacks compatibility with complex peripherals and direct memory access, whereas hardware-in-loop solutions often require custom hardware only available for academic use. To solve these challenges in rehosting frameworks, microAFL or mAFL proposes decoupling the execution engine from the fuzzer, which lets go of the emulator. In this framework, the execution of the target binary happens natively on the microcontroller, while the bulk of the fuzzing duties are done on the more powerful workstation using the popular AFL fuzzer. As such, the workstation now does not have to approximate the behavior of the hardware while observing real-time effects of complex interactions with the microcontroller peripherals. The fuzzing loop proposed by microAFL now looks something like this. There are two components, the fuzzing manager, which runs on the workstation, and the execution engine, which runs on the microcontroller. A debugger dongle bridges the microcontroller to the host PC, which runs the genetic AFL algorithm for coverage analysis, mutation, and test case generation. Now, to avoid instrumenting the binary, mAFL leverages embedded trace macrocell found in ARM devices to trace code coverage. To comply with AFL bitmap-based coverage analysis, this necessitates three new components: an online trace collector running on the microcontroller, an offline trace analyzer running on the host, and trace filters which are present in both the microcontroller and the host, as the figure shows. So, why does mAFL not opt for coverage instrumentation like other fuzzers? First, instrumenting a binary with coverage hooks increases its size, which puts strain on the limited memory and slower operating speeds of microcontrollers. Secondly, at the time of writing this paper, no appropriate binary rewriting tools existed that reliably rewrite compiled binaries with coverage instrumentation for these microcontrollers. As such, the authors of this paper propose using embedded trace macrocell technology provided by ARM for control flow analysis on ARM embedded devices. They repurpose the ETM trace to extract code coverage information that is compatible with AFL. The hardware directly generates and communicates this ETM trace to the host at real time while the target is executing. The offline trace analyzer runs on the PC and processes the raw ETM data. The result is provided to AFL to maintain the bitmap of code coverage. Decoding the raw ETM data to get the branch information is expensive since it needs to disassemble the firmware and align the instructions with the raw trace. mAFL solves this problem by using a kind of special basic block generated at runtime called the linear code sequence and jump basic block. It is an instruction sequence that starts from the last taken branch and ends at the subsequent branch instruction which is actually taken. This information can be extracted from the raw ETM trace without requiring any disassembling and decoding via the branch base address and instruction sequence bitstream present in the ETM trace. However, it must be noted that this leads to a different bitmap than AFL, even though it is compatible with AFL and retains similar path sensitivity. Finally, ARM supports streaming the trace data to an external debugger via a physical parallel port called Cortex Debug plus ETM connector, which is what mAFL opts for. Additionally, mAFL transmits the subsequent test case in the background while the target is running against the current test case. They further conduct the analysis of the previous test case on the host in parallel with the target execution. By scheduling all these tasks in a pipeline, mAFL achieves optimized performance. Another optimization performed by mAFL is filtering the ETM trace packets. Raw ETM packets contain a lot of data besides information relevant to branch coverage. The authors find that mAFL aggressively needs to filter ETM packets to deal with too much data and too little bandwidth. To this end, they use the data watchpoint and trace unit to filter irrelevant ETM packets in real time on the microcontroller. These include address-based filters and event-based filters. Address-based filters allow analysts to specify a continuous code region to be traced. It works the best when we are interested in a particular library. mAFL also supports event-based filters, in which certain events trigger the on or off switch of the ETM. The event can either be executing an instruction in a particular memory range or reading or writing a particular value from or to a particular address. They use the online trace filter to filter out the tracing of test case independent code such as booting firmware. mAFL also requires an offline trace filter to filter out the tracing of the exceptions, as exceptions are non-deterministic and add instability to the fuzzer. This is done offline as it requires more expensive analysis of exception information. This figure shows the experimental setup of mAFL. mAFL is built on top of the AFL fuzzer version 2.56. For the debug dongle, the authors used the Seger JTrace Pro. Using this setup, they first test vendor-provided software development kits, focusing on peripheral applications such as vendor SDKs, mostly focusing on peripheral drivers, and these applications include Fibonacci, I2C, UART, USB, SD card, Ethernet, and MMCAU operations. Also, for the microcontrollers, they evaluate the benchmarks on two microcontroller platforms. One is the NXP based microcontroller, and the other one is an STM32 based evaluation board. Coming to the evaluation, the high-level research questions addressed in the paper include: does the linear code sequence and jump basic block based approach that directly processes raw ETM trace improve performance compared to approaches that fully recover the instruction flow? Do online filters help to improve the performance of mAFL? How much overhead does mAFL introduce to each sub-process of a single round of fuzzing? What is the overall performance of mAFL? How does it compare to existing work? And finally, how effective is mAFL in locating bugs in the peripheral drivers of real-world firmware? I don't know why these bullet points just decided to malfunction, but yeah, these should be like 6 questions that we're going to talk about now. So, the first question, does LCSAJ-BB based approach that directly processes raw ATM trace improve performance compared to approaches that fully recover the instruction flow? Well, the table shows the executions per hour for both the approaches, as highlighted by red boxes. The authors show that LCSAJ-BB based approach is up to 4.8 times faster than disassembly and decode based approach. Now, do online filters really help to improve the performance of mAFL? As the table shows, online filters improve the performance of mAFL across all the evaluated benchmarks. This is because without filters, ETM needs to collect the entire instruction trace beginning from reset ISR to the end of each run, which not only increases the burden of the debug dongle in transferring the raw trace, but also requires more time for the offline decoder to decode and map them into the bitmap. For large and complex benchmarks such as USB, UR, such as USB, SD card, and ENIC, as shown here, the difference is small as the target execution time is longer, amortizing the overhead. Now, how much overhead does mAFL introduce to each sub-process of a single round of fuzzing? In the chart, reset to start measures time from device booting to fuzzing start point. Start trace measures time spent on transmitting a test case from host to device, as well as configuring the ETM and DWT functions. Start to end is time spent from fuzzing start point to end point. Stop trace is the time spent on disabling the ETM trace and waiting for completion of ETM trace transmission. Finally, analysis is the time spent on analyzing the ETM packets. As you can see, the execution time for reset to start and start trace stays stable across benchmarks, but execution time for other sub-processes increases as complexity of firmware increases. This is because more ETM packets were generated in more sophisticated firmware samples, consequently increasing their overhead. So, the fourth research question which they address is what is the overall performance of UFL, right? It's an important question. And as you can see, for this experiment, the authors first tested each benchmark for 2 days. From the experiments, we can see that mAFL is able to achieve up to 30 execs per second for the benchmark suite, right? For the I2C benchmark. As expected, mAFL achieves slower fuzzing speeds for complex peripheral drivers such as USB, SD card, and Ethernet. It must be noted that the debug dongle does not support very large traces such as 200 megabytes or larger for complex peripheral firmware. So, in this case, they discard the traces for those test cases when possible, which incurs additional overhead on their fuzzing speed, as we can see here. Large traces that cannot be detected corrupt the fuzzing feedback, leading to a large number of false positives in some cases, right? Next, how does the overall performance of mAFL compare with existing works? For the study, they considered 3 other works where P2IM and microEMU represent rehosting approaches based on emulation. Avatar Square, on the other hand, is the closest work to microFL at the time. It is a rehosting approach based on forwarding complex interactions such as booting and peripherals to real hardware and symbolic execution. MicroFL outperforms Avatar Square, but is much slower in comparison to emulation-based approaches as they run natively on the host PC. So, how effective is mAFL in locating bugs in peripheral drivers of real-world firmware? To prove the efficacy of mAFL in fuzzing real-world embedded peripheral driver firmware, the authors conduct multiple two-day fuzzing campaigns with vendor-provided SDKs for peripheral applications of USB, SD card, and Ethernet. The figure shows the operations performed by their USB enumeration benchmark. Their trials led them to discover 13 zero-day bugs resulting in 8 CVEs in USB firmwares from NXP and STM. These include unsanitized length attributes and descriptors, missed hardware support checks, illogical endpoint address, and unchecked polling interval. So, based on this talk, where do you think rehosting approaches outshine semi-hosting? When scalability is a concern, right? Software emulation is well known for its independence from the physical platform, which in turn facilitates advanced analysis with much more flexibility and scalability. While semi-hosting provides higher fidelity, it is not as scalable as software emulation. So, when do you think semi-hosting outshines rehosting? When fidelity, observability, and compatibility are preferred over scalability. Semi-hosting allows true responses from real hardware and supports testing of complex peripherals with high fidelity. Although semi-hosting techniques currently offer lower speeds compared to software emulation approaches, they are the only methods that allow testing of complex peripherals. Next, based on all of our discussion, what do you think are some shortcomings of mAFL style semi-hosted fuzzing? Well, first is obviously while mAFL allows fuzz testing directly on real hardware, it is only specific to ARM devices that provide support for ETM tracing. It will not work with any other vendor or ARM devices that do not support ETM traces, unless ETM or similar technology is supported by those vendors. Moreover, it faces technical issues due to lack of debug dongle support for large execution traces, leading to loss of fidelity and observability, which is their main advantage over software emulation techniques. While ETMs avoid binary rewriting, they do not address the large overhead of communicating between the device and the host, which is the bottleneck of semi-hosted approaches. Finally, although the authors propose mAFL as a fuzz testing solution for stripped binaries, it only applies to specific library code as some source code is still needed for setting up harnesses and instrumenting test case hooks. So, based on this discussion, I want to leave you with a question. Given the shortcomings of mAFL, what would you do differently to improve the semi-hosting fuzzing framework? In summary, mAFL presents a semi-hosted framework that enables native execution of target binaries on the MCU, achieving high fidelity of hardware, observability of faults, and compatibility with peripherals. This allows mAFL to identify vulnerabilities in complex peripheral drivers not supported by emulation-based solutions. While mAFL accounts for resource constraints and bare metal nature of MCU firmware, its solution is specific to ARM devices that support ETM tracing, not taking into account diversity of hardware in microcontrollers. This motivates a more general approach to semi-hosting that is compatible or at least portable to a diverse set of microcontrollers from different manufacturers. Well, thank you for tuning in. This was my talk.